What we're going to go through now is talking about three dimensions more formally. So we're going to start by just going back to two dimensions. So recall in the XY coordinate system, or R2, we needed two values to plot a point. So we had our two axes, the X and the Y axis, and we needed those two values, the first one being X, the second being Y. And then we had that point where those two axes meet, which was 0, 0, or the origin. So pretty much at this point, we're going to assume that we're working in 3-dimension. So this space in 2D is called our XY plane. So from now on, we're going to call this the XY plane. So in space, we need that triple, or 3 dimensions. We can represent any point by an ordered triple, which is going to be some ABC of real numbers. So to give you our visual, and I'm going to take my time with this, again, remember our XY plane is that 2-dimensional space. Here is the X, here is the Y, and then Z is going to be to the sky. So these particular 3 axes that point in that positive direction are called our coordinate axes. Okay. The origin is the point at the center still. Let's see, where can I make this? Let's do it like this. And it has the coordinates 0, 0, 0. So you move nothing in any direction. Now, what we typically need is we need all of the other negative cases. So what we like to do is instead draw these as dashed lines. So let's see, can I change this easily here? Yeah, there we go. So going down will be the negative Z, and then going back here is the negative Y axis. Okay. So this dashed line represents the negative half. So while you're getting started out, it makes a lot of sense really to just draw the positive ones, because if you have to draw these negative values, it gets really muddled. And while you're starting out, you want to try to keep it as clean as possible. Now within here, we told you that the XY plane is exactly that 2-dimensional space. So we really have a couple different planes that are going to be important for us. So these coordinate axes determine what we call our coordinate planes. So a plane, we'll get into detail about that very soon, but it's just that flat surface. So 2D is the XY plane. And in that point, you're assuming that your Z value does not exist, or you can think of Z as equaling 0. So what I'm going to do is I'm going to go ahead and I'm going to copy this picture just to make life a little bit easier and just delete some of this stuff on here. I'm not going to worry about the origin too much. Ignore all of these and let's go ahead and fill in our pieces. So we have technically 3 coordinate planes going on here. Can I fit it all? Great. Let's move this over a little bit. Okay. So our first plane is the XY plane. Which is the XY coordinate plane. This contains the X and the Y axes. So here, your value of Z is going to equal 0. So if I tried to draw this in, that's going to be this flat surface. Okay. Then our next coordinate plane is going to be the XZ plane. And this is where your Y value is equal to 0. So instead, that's going to contain both the X and the Z axes. So imagine basically like a sheet of paper that's going through both of those axes. And then finally, we have our YZ plane. And as you kind of can make an assumption, the XY plane Z is equal to 0, XZ, Y is equal to 0. The missing variable here is X, so we assume X is equal to 0 when we're on this plane. And this has to contain the Z and the Y axes. So on this image, it is this flat surface that connects those two. Okay. So you can think of a plane as just really a sheet of paper passing through these. And we'll talk about other planes where they're at different angles and so on. But these 3 coordinate axes are going to be really helpful for us, especially when we start graphing the 3-dimensional stuff. Now, the other nice thing that happens with these, we know when we're dealing with 2 dimensions, the X and Y axes split that 2-dimensional surface into 4 quadrants. Here, we actually split it into 8 pieces. So it's a little hard to graph, but you can think of, you have the 4 that are sitting in the top in the positive Z axis, and then those 4 from the XY plane being split up. And then you have the 4 underneath that are negative. So since we have 8, we call these octants. So the 3 coordinate planes divide space into 8 parts, which are called octants. Okay. So just to go back up here for a second, we know this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. So when you're dealing in 3-dimension, you basically have that third axis going above and you have that third axis going below. So you have those 4 quadrants, and then on each one of those quadrants, you have your Z values either positive or negative. So since our first quadrant is where X and Y are positive, the first octant is going to be the same kind of thing. So here, the first octant is determined by all of the positive axes. And then you move counterclockwise, and then you go underneath. So where X and Y are positive, but Z is negative, that would be your 5th octant, okay? So now we can start talking about how to kind of draw these visually so we can see a little bit better what's going on. So if we're given a point P in space, we represent P by the ordered triple. Which will have coordinates, we'll call them A, B, C for now. So the way I'm going to go ahead and graph this is I'm just going to worry about the positive components, and I'm going to just assume A, B, and C are positive numbers. Again, just to make my life a little bit easier. So what I'm going to do is I'm going to move a distance of A in the X direction. And again, I'm going to just assume it's a positive value. So we go out to here, a distance of A. Then I'm going to move a distance of B in the Y direction. So that's going to run parallel to the Y axis. And the length of this side would be B. And then finally, we move a distance of C in the Z direction. And so that is going to run parallel to the Z axis. And the length of this side will be C. So in return, I get this final point. Let's use a color that stands out a little bit better, which is P, that's represented by ABC. So it's really difficult if I just give you a point for you to try to find the coordinates. Instead, we're going to have to plot them individually. So it's not like way back in intermediate algebra when you plot a point, here, tell me what the coordinates are. This is a little complicated because you can't always tell, okay, is this forward? Is it backwards? It's really difficult to draw three-dimension in two. All right, the nice thing though is just like we call these the rectangular coordinate system, because every point in the xy plane forms a rectangle with the origin. The same kind of idea happens here, but because it's 3D, it's not a rectangle, it's a three-dimensional object, so it's going to be a rectangular box. So each point P determines a rectangular box. So let's go ahead and pick our point P, and I'll show you how that box is ultimately formed. So let's say point P is right here, and it has coordinates A, B, C. What I can do to draw this box is I'm basically going to drop perpendiculars back to each of my coordinate planes. So the first perpendicular I'm going to drop down is to the XY axis here. And I'm going to call this point Q. So this point is on the XY plane. It means I'm not touching the X or Y values, but I'm making that value of Z to be 0. Then I can form another point by dropping it to the XZ axis or XZ plane. So this point here, let's call it S. And if I'm in the XZ plane, that means my Y coordinate is equal to 0. So we're not touching anything else except we're changing the Y coordinate to drop it down to be perpendicular. And then finally, if we drop a perpendicular back to the YZ plane, let's call this point R, then all we're doing is making X to be 0, and the other values stay exactly the same. And so in the end, what is formed is a nice box. So let's go ahead and use some dotted lines to make this a little bit nicer. So now I can keep dropping perpendiculars down to all of our different axes. And you can see we get this nice box that is formed. And then that last side is going to be back there with the origin. So filling in just some labels for each of these. This point here is how far you move in the X direction. This point here is how far you move in the Y. And then this is how far you move in the Z. And then that last point in the back is indeed our origin. So we make a nice box here. So these 3 points are important to us because basically the idea behind these is if you're standing right at your point P and you're looking straight down to the XY plane, you're seeing what's happening. What does this look like just in the XY? If I'm standing here and I face in the direction of the YZ plane, this is what that point looks like. And then same thing back here, when I'm standing and looking at the XZ plane, I'm getting this visual. It's like you're taking a bird's eye view from that perspective. So there's a special idea that this is called when we're seeing what is happening from that vantage point into that plane, we call it a projection. So again, if you're going onto linear algebra, you'll talk about this more. You'll talk about projections of one vector onto another. We're going to skip that in this class, but you can look it in your textbook. It is sometimes taught. So here, if we drop a perpendicular line from P to the XY plane, we get this point Q with coordinates A, B, 0. And so again, this is just if I'm standing at point B and I'm looking directly in the direction of the XY axis, this is the image that I'm seeing in that two-dimensional surface. So this specifically is called the projection of P onto the XY plane. So that concept of projection is just seeing what image do you see when you move it or when you're looking into that other vantage point. Okay. And then in a similar manner, we have these other two projections of the point onto the different planes. So I'm terrible at saying this word similarly. Or similarly, we can drop perpendicular lines to the other coordinate planes to get the following points. Okay. So going back up here, R is the projection onto the YZ plane, and that's where we make our X equal to 0. So R has the coordinate 0, BC. This is the projection of P onto the YZ plane. And then S has the coordinates A, 0, C. So in this case, you're removing that y component. So this is the projection of P onto the xz plane. Okay. So another way you can also think about these projections, because you're missing that y component, it's basically like if I'm standing on the y-axis and I'm looking straight down into the xz plane. This is that two-dimensional point that I'm seeing, ignoring my y component. Okay. So let's try an example. Let's consider the point 1, 2, 3. First thing we're going to do is we're going to draw the rectangular box determined by the point. And we're going to fill in all of the different vertices of that box as well. So we're going to go ahead and draw our 3 axes. X, Y, and Z are all positive. So I'm only going to worry about drawing the positive axes here. We need to go out a distance of 3, so I'm going to go ahead and just draw a marking of 3 in each direction. Okay. Now what I'm going to do is I'm going to start by figuring out where this point particularly lies. And really in the process of doing so, I'm actually going to end up finding a bunch of my different vertices. So we're going to start right here at the origin, which has that point 0, 0, 0. Now in my x, I'm going to have to go out a distance of 1. So we go out right to here. In my y, I have to go a distance of 2, which means I have to go this length. So really what I need to do to draw this is I need to draw that same length so that it would make a box here. So it runs parallel. And then in my z coordinate, I have to go up a distance of 3, which means I have to go this high. And so roughly that's about to here. So this would be where our point P is, which has the coordinates 1, 2, 3. Now I'm going to go ahead and actually solidify in this box. And again, you can do this along the way, but let's make this a little bit smaller here. Okay. So I'm going to go ahead and drop that perpendicular line down to the XY plane. And this point here would be the point 1, 2, 0. Then I'm going to go ahead and I'm going to drop 1 back. And that means I'm ignoring the x component. So this is the point 0, 2, 3. And then last but not least, we drop 1 directly back to the xz plane. So this point here would be 1, 0, 3. And then filling in all the other pieces. Again, do the best you can. We get our box here, got our box in the back, straight line down, straight line back, straight line over here. You can see it's not quite perfect, but that's okay. Again, it's human error. So this point here would be 1, 0, 0. This point here is just on the y-axis, so it's 0, 2, 0. And right back here is just on the z, so it's 0, 0, 3. So that is our box that is formed by this particular point. Now for part B, we want to find the projections onto the coordinate planes. Okay. So if we start with the xy plane, your z is equal to 0. So this projection is 1, 2, 0. If I want the xz plane, we just set y equal to 0. So 1, 0, 3. And then finally, if we want the yz plane, then we set x equal to 0. So those are our 3 projections. Okay. Now what we're going to do just for the last bit is again kind of just extend some of the ideas that we're used to in 2 dimensions into 3. So we're going to start with our distance formula now that we have a solid terminology and classification for points. And again, this is just a natural extension from our normal distance formula in 2D. So here, the distance, let's say between the points P to Q, the way we represent distance is the magnitude. So again, I'm going to use those absolute values to represent the magnitude of this distance. So this distance between 2 points, P, which we'll say has coordinates x, y, z, and the point Q, which we'll say has coordinates a, b, c, is given by the following. Normally, when we find the distance, we take the difference in x values squared, we add the difference in y values squared, and then we take a square root. So when you're dealing with 3 dimensions, you just add on that third component, the difference in z values squared. And it's still under a giant square root. So really natural next extension. You can do the same thing to prove it. I'm going to skip it because I think at this point you can see it's kind of straightforward, but you're going to just use Pythagorean theorem to calculate the distance between these two, and it's just going to rely on creating some triangles from here. So it's a really nice extension. So I think you could easily calculate a distance. So instead, what I'm going to do, instead of just straightforward asking you to find the distance between 2 points, we're going to instead determine if the points lie on a straight line. In 2D, not too hard of a question. You could definitely plot it in like an online software and see if they're collinear or not. You could also easily come up with the equation of between 2 of the points and then see does the third one fit into that equation. But the second you add that third dimension, I definitely can't visually do this. So instead, I've got to come up with something else. So let's say the point has coordinates 0, negative 5, 5. The point B has 1, negative 2, 4 as its coordinates. And C is the point 3, 4, 2. Okay. So visually, I don't know what these are going to look like in 3 dimensions, and I'm sure not going to sit here and try to plot them. So instead, all I do know is if these lie on a straight line, maybe my point B is right here, it would look something like this. Okay. So what I can do, because I know how to calculate the distance between 2 points, this distance here is the distance from A to B. This distance here is from B to C. And if I add those together, it better give me this longer distance from A 2c. So if the points lie on a straight line, then the distance from A to B plus the distance from B to C will equal the total distance from A to C. Of course, I'm just assuming here that A to C is the longest distance, but basically you'd have to be able to add two of the smaller ones and get the third larger distance. But if this wasn't the case, if they don't add together, we'd have the following. It would form some kind of triangle instead. So maybe here's A, B, C. This side here would be the distance from A to B. This side here would be the distance from B to C, and then A to C. And we know then if I add these two together, AB plus BC, it would be bigger than the hypotenuse of the triangle. So when you add the two smaller sides together, it's larger than the third one. So ultimately here, there would be a more complicated relationship. With the three sides. So instead, what I'm going to do is I'm going to find the distance from A to B to C, and then also from B to C. And can I come up with some kind of nice relationship between the two? So let's go ahead, just for sake here, let's copy these down so I don't have to keep looking up at the top. Here are 3 points. So let's start with the distance from A to B. So I'm going to write my square root at the end, but we do the difference in x values. So 0 and 1, difference in y values, and you have that minus minus, so this turns to plus 2, and then the difference in z values squared, all under a square root. So this will be negative 1 squared turns to positive 1. And then you have negative 3 squared, that becomes positive 9. And then 1 squared is 1. So this side length ends up being root 11. Now if I find the distance from B to C, same thing, difference in x values is 1 minus 3. Difference in y values, negative 2 minus 4. And then difference in v values, which is 4 minus 2. So going through that, 1 minus 3 is negative 2. When you square it, it's positive 4. Negative 2 minus 4 is negative 6. Square it is 36. 4 minus 2 is 2. And squared is 4. So when we add those together, 4 plus 36 is 40. Add another 4. This is root 44. Now the thing is, I do need to be able to add these side lengths together. So here I do want to simplify my radical. And the inside you can write as 4 times 11. So the 4 has the 2 pop out, and this is 2 root 11. And then last but not least, we want to find the distance from A to C. So we've got 0 minus 3 for the x values, negative 5 minus 4 for the y, and 5 minus 2 for the z, all under a square root. Negative 3 squared gives us positive 9. Then negative 5 minus 4 is negative 9. Squared will be 81. 5 minus 2 is 3, so squared is 9. 9 plus 81 is 90. Add another 9 to that, and that is root 99. So breaking that down, that's 9 times 11. So this pops out as 3 root 11. So this here is the longest side, looking at all of these. So I want to see, do the two smaller sides add up to that longer side? And indeed, that's the case. So here, since we add AB and BC, that gives us root 11 plus 2 root 11, 3 root 11. It's indeed the longer side. We can say these points lie on a straight line. What we can also say actually is these are collinear. To indicate they lie on a straight line. Okay. Now the very last thing we're going to talk about is we've got our distance formula extending to 3 dimensions. What happens when I extend my circle into that 3rd dimension? We're going to talk heavily in a future section about all of the different types of graphs that we have. But again, it's a really nice natural extension. So when you take a 2-dimensional circle and put it in 3D, what you're going to get is going to be a sphere. So a sphere is the set of all points x, y, z that are a fixed distance r from a given point which is going to be that center. So remember, normally we use HK for the center, but when we add that third, HKL. And I like to use a cursive L so I don't mistake it for a 1. Okay. So this comes naturally just from that distance formula. The distance is a fixed value. So here in that case, it's what we call our radius. So our radius squared is just that fixed distance from that center point. And then we just move that square root over to make it a little bit nicer. So that's why it gets in this section. But again, we're going to talk about circles very soon in the future, more in detail. But this distance r is the radius and this point HKL is the center. So the equation of our sphere is we take x and subtract the x coordinate of the center, square it, y minus the y coordinate of the center, z minus the z coordinate of the center. And that equals the radius squared. So really you're just adding on that third component. So this is the equation of the sphere specifically where our radius is a positive number, because again, it is that distance. So I just have one last example for you. I think you're probably perfectly capable of creating the equation of a sphere. So what I'm going to do instead is we're going to find the center and radius to just go over that, completing the square if you don't remember. So here we're going to find the center and radius of the sphere. And we're given the equation x squared plus y squared plus z squared plus 8x minus 6y plus 2z plus 17 equals 0. So what I need to do to complete this square is I've got to group all of my x's, all of my y's, all of my z's together, and I want to move the constant over to the other side. And I want to give myself a little bit of room. So we have x squared and we have 8x. Then our next one we have y squared and minus 6y. So I'm going to save some space there. And then last but not least, we have z squared plus 2z. So again, give myself a little bit of space. And then on the right-hand side, when we move that 17 over, it gives us negative 17. I'm going to need a little bit of extra room over there. So I'm going to go ahead and group these. I don't have to factor anything out, thankfully. They all have a 1 in front of that squared component. So what I need to do is I need to add a number here so that it's a perfect square, and it's going to depend on that coefficient in front of x. So what I need to do is I need to take this number 8, divide it by 2, which is 4, and then I'm going to go ahead and square it. So what I need to add here is really 16, because what that does is it makes it so that this is x plus 4 times x plus 4. So when you FOIL that out, it gives you everything. So this makes it x plus 4 squared. But if I'm adding 16 on this side, I've got to do the same thing on the right to balance this out. Now here for the y component, again, it's going to depend on this number. So negative 6 cut in half is negative 3. When I square that, I need to add a 9 here. Because what that does is it makes it so that this is y minus 3 squared. And again, you could set it up just as you're foiling or unfactoring this and reversing that foiling process. But if I add 9 there, it means I need to add a 9 to this side as well. And then last but not least, for the z component, cut that in half, it's 1, square it, it gives you a plus 1. So I do the same thing over here. And that makes this factor nicely to z plus 1 squared. So the left-hand side fully factored. Then when I go onto this right-hand side, negative 17 plus 16 is negative 1. Plus that 1 cancels. This really ends up simplifying to 9. So I've got the equation of my circle all set up in that what we call standard form. So I can immediately pick off that my center is the triple with opposite signs. So my x coordinate of the center is negative 4, my y coordinate is positive 3, and my z coordinate is negative 1. And then my radius of the circle deals with 9, that is the radius squared. So my radius r is going to be 3.